Hello everyone. In this session, we are going to explore something very interesting that usually works silently behind every computer, laptop, mobile phone, ATM machine, even smart cars. The topic that we are going to address is operating system architectures. Now, when we say architecture, what comes into your mind? Think about buildings around Pune city. If you go near Shaniwar Wada, the architecture is very different from the modern buildings in Hinjawadi IT Park. Both buildings serve peoples, but their internal design is different. Exactly the same thing happens with the operating systems. An operating system is not just one big program. Inside, there is a structure, there is a design, there is arrangement of components that decides how everything works together. Just like an architect designs a building carefully, a computer programmer or scientist design the internal structure of an operating system. Today, we will explore three very important architectures: monolithic, microkernel, and layered architecture. You can imagine this session as a journey inside the brain of an operating system. And by the end of this session, wherever you start your laptop or open an app on your phone, you will remember that there is a very carefully designed architecture making everything run smoothly or work smoothly. So let us address now what is inside an operating system. Let us begin with again a simple question. What exactly does an operating system do? Think of the operating system as the brain of a computer. Just like our brain controls our body parts, such as hands, legs, and eyes, the operating system controls hardware as well as software. For example, when you open a browser, when you play a video, when you save a file, when you connect a printer, the operating system is quietly coordinating everything. Let us imagine a real life example from Savitribai Phule University campus. Suppose there is a large university festival happening in the campus. Thousands of students arrive. Different departments conduct events. Security controls entry. Food stalls serve people. Someone must coordinate everything. And that role is similar to what operating system does. Now, the important question is this: how is this coordination organized internally? How are the responsibilities divided? And that internal design is called as operating system architecture. As I stated, we will be exploring three famous ways of organizing an operating system: monolithic architecture, macrokernel architecture, and layer architecture. Each one solves the same problem but in a different way. Let us start by addressing monolithic architecture. This is all-in-one powerhouse. Let us start with this first architecture. The word monolithic means one large block. Imagine you go to a small restaurant in Pune where one person is doing everything: taking orders, cooking food, handling billing, serving customers. Everything is happening inside one system. And that is exactly how a monolithic operating system works. Inside a monolithic architecture, the entire operating system runs as one user program or one large program. All major parts of the operating system exist together in the same space. And these parts include, say, device drivers, file system management, memory management, process scheduling, input and output operations, security and networking, and so on. All of them live together inside the kernel space. Kernel space means the most powerful part of the operating system because everything is in the same place. Communication becomes extremely fast. If one component needs help from another component, it simply calls the function directly. No complicated communication is needed here. And that is why monolithic systems are very fast. But there is also a risk. Since everything is connected closely, if one part fails, it may affect the entire system. Think of it like a crowded traffic junction at at Pune University Square. If one truck breaks down in the middle of the university circle, suddenly the entire traffic can stop. And that is the risk of monolithic architecture. A famous example of this architecture is the Linux kernel. Linux powers many systems today, the servers, supercomputers, Android phones, cloud infrastructure. It delivers excellent performance because its design reduces communication overhead. Now, why monolithic kernels feel fast? Now, let us understand why this happens. Inside this architecture, everything runs in the same memory space, as I stated. This means components talk to each other using direct function calls. Think of two teachers in the same room in SPPU campus, computer science department. If one professor needs help, they simply ask the colleague sitting next to them. The answer comes immediately. But imagine if the colleague was in another building, you might need to send an email, wait for a reply, maybe schedule a meeting. That delay is avoided in monolithic systems. Because everything is inside one address space, operations happen very quickly. And however, there was one major challenge earlier. If developers wanted to add a new feature or a driver, they often had to recompile the entire kernel. That means rebuilding the whole operating system. Imagine if Pune Municipal Corporation had to rebuild the entire city every time they wanted to add a new road. Clearly, that would be very difficult. So later, operating systems introduced kernel modules. Modules allow features to be added dynamically without rebuilding the entire kernel. And this made monolithic systems very flexible. So the monolithic architecture is very likely as a highly efficient team sitting together in one room. Work happens quickly. But if someone or something goes wrong inside that room, everyone gets affected. Now, microkernel architecture, minimalist and modular. Let us move to this second architecture known as microkernel architecture. The word micro means small. It is a design where the kernel is intentionally kept very small. Only the most essential services are inside the kernel. And these essential services include, say, for example, process scheduling, inter-process communication, basic memory management. Everything else runs outside the kernel. Yes, outside. Components like device drivers, file systems, network services run as separate programs in user space. Why do we do this? Because isolation increases availability as well as reliability. Imagine a scenario in Pune city. Suppose one department in the municipal corporation makes a mistake. In a well-organized system, that mistake should not shut down the entire city administration. Each department should operate independently, and microkernel follows the same idea. If a device driver crashes, it does not destroy the whole operating system. Only that small component restarts. The core kernel remains safe. One famous operating system using microkernel architecture is QNX. Neutrino. QNX is widely used in automotive systems. Many modern cars rely on it for navigation systems, entertainment systems, and safety features. Because in a car, reliability is extremely important. You cannot afford a system crash while driving on, let us say, Mumbai-Pune Expressway. So microkernel architecture focuses strongly on stability and safety. Now, what are the trade-offs? Flexibility versus speed. Now, every design has advantages and disadvantages. Microkernel is excellent for reliability, but there is a cost. Remember that many services are now outside the kernel. So, when one component wants to talk to another component, they must send messages. And this is called as message passing. Imagine department inside Pune Municipal Corporation communicating through official letters. A message goes from one office to another office. Then a response comes back. This process takes time. Similarly, in microkernel systems, communication between services requires message exchange. Because of this extra communication, performance can be slower. However, the benefits are significant. Isolation improves stability. Customization becomes very easy. Developers can modify individual components without touching the entire system. So we can summarize like this. Performance overhead may increase, reliability improves significantly, maintenance becomes easier, customization becomes easier. Think of it like a well-organized city administration. Each department works independently, but communication through clear channels. The system may be slightly slower, but it is far safe and more manageable. So let us address the third one, the layered architecture. Building the OS like a layered cake. Now let us explore this important architecture. Imagine a layered cake. Each layer sits on top of another layer. That is exactly how this operating system design is given. The operating system is divided into multiple layers. Each layer performs a specific role. Let us go from top to bottom. The top layer is the user interface. This is where user interacts with the system. For example, when students in SPPU open their laptops and see the desktop environment, below that comes a file system layer. This layer manages files and storage. So when you save assignments or projects, this layer organizes the data. Below that, there is a memory management layer. It decides how RAM is allocated to different programs. Below that, there is a process control. This layer schedules tasks and ensures multiple programs run smoothly. Finally, at the bottom, there is a hardware layer. This layer interacts directly with the physical components such as CPU, memory, disk, and devices. Each layer only communicates with the layer directly below it. And this creates a structured and organized systems. A classic example of this approach is Unix operating system design philosophy. Now let us understand the answer with respect to an important question. Why layered design still matters in current era, that is 2026. You might ask this as an important question. Why do we still use this? The answer is organization or organize clarity. Operating systems are extremely complex. Millions of lines of code exist inside them. The layered architecture helps managing this complexity. Developers can focus on one layer at a time. For example, a developer working on file system does not need to worry about hardware drivers. Each layer hides its internal complexity. And this concept is called as abstraction. Think of it like academic structure in a university. Students interact with professors. Professors coordinate with department heads. Department heads interact with the university administration. Each level focuses on its own responsibility. However, layered architecture can sometimes reduce performance because data must travel through several layers before reaching hardware. It is like passing a message through several peoples in a line. The message eventually reaches the destination, but it takes slightly longer. Even then, layered design remains very useful because it brings the order and clarity to the complex systems. Let us understand the real world impact. Choosing the right architecture. And this is most important question. Which architecture is best? The answer is simple. There is no universal best architecture. The choice depends on the goal of the system. Monolithic architecture is excellent when speed and performance critical. And this is why the system like Linux and Windows use designs influenced by the monolithic kernels. These operating systems power servers, laptops, cloud systems where performance matters. Microkernel architectures shines in safety critical environments. Example like automobiles, medical devices, aircraft control systems. In these environments, reliability is more important than raw speed. Layered architecture helps managing complex software systems. It makes development and maintenance very easy. Large scale systems often adopt the layered ideas to maintain the order. So the decision depends on priorities. What are your priorities? So if reliability is the top priority, choose microkernel. And if organization and maintainability are the focus, then choose layered architecture. So the OS architecture balances the act. Let us bring everything together now. Operating system architecture is about how the internal parts of the operating systems are organized. We explored three major architectures. Monolithic architecture, where everything works together in one powerful unit. Microkernel architecture, where the kernel is small and services run independently. Layered architecture, where the system is organized in a structured layer. Each design has its strength and limitations. Some prioritize speed, some prioritize safety, and some of them prioritize organization. The beauty of computer science is that different designs solve different problems. So next time you start your laptop in your hostel room or lab in computer science department, or when you unlock your smartphone in Pune metro, remember something interesting. Behind that smooth experience, there is an invisible architecture carefully coordinating millions of operations every second. Understanding these architectures helps us appreciating the brilliance, the engineering behind the modern computing. And who knows, maybe someday some of you will design the next generation operating system architecture for the world. Thank you.